Assalamualaikum and a very good day. We are from Group 4 are going to present the electromagnetic blood flow meter.
Our group members consist of Darshan, Aina, Shihan, Huiying, and Chiayi.
My name is Nura Aina Shamimi and I am going to present the introduction. What is the electromagnetic flow meter? It is used to measure blood flow in blood vessel throughout the circulatory system. It is also based on Faraday's law of electromagnetic induction discovered in the 19th century. What is Faraday's first law? Faraday's first law is the law of electromagnetism behind the electromagnetic blood flow meter. Whenever a conductor is placed in a varying magnetic field, an electromotive force is induced. If the conductor circuit is closed, a current is induced, which is called the induced current.
Hello everyone, I'm Huiying and I'll be explaining about the working principle of electromagnetic blood flow meter. The electromagnetic blood flow meter works on the principle of Faraday's law of electromagnetic induction, which is explained in the previous slide. This law states that when the conductive liquid passes through the magnetic field, the voltage induces across the conductor. So the magnetic field is generated by the coil, which is mounted on the external metallic body of the pipe. The liquid acts as a conductor and when passes through the magnetic field, induces the voltage across the coil. The magnitude of the voltage across the coil depends on the velocity of the liquid, and it is directly proportional to the velocity, length of the conductor, and also the strength of magnetic field.
Now let us look at the structural construction of electromagnetic flow meter. For this meter, there are electrically insulated or non-conducting pipe are used, which in this case fiberglass is commonly used in all electromagnetic flow meter. So there are a pair of electrodes which is mounted opposite to each other and flushes the inside wall carrying the fluid, which in this case human blood. So that's how the flow of this blood is measured. In the figure we have provided, we can clearly see that there are two electrodes are placed at right angles to the plane of the magnetic flux lines. These magnetic flux lines are produced by the electromagnet which are wounded with the coil. Now let's look at how this electromagnetic flow meter measures the flow rate of blood. So when a conductive fluid, which in this case human blood, is passed through the pipe, the motion relative to magnetic field produces an induced EMF, electromotive force, proportional to the velocity of the fluid. So this is the formula that is related to this, and this formula obeys Faraday's law, which states that the electromotive force induced is equal to the product of magnetic flux density, the length of the conductor, and the velocity of the conductor.
For conclusion, we understood the concept of Faraday's first law and electromagnetic induction. We also apply electromagnetic induction into real-life biomedical engineering related examples.
A very good day to Dr. Raimi and my fellow friends. I'm Kushahan from Group 4. Now, me and Chu Chieyi will present about our demo video. The experiment we carry out is about the electromagnetic induction based on Faraday's law. Let's see what are the materials and apparatus we needed for this experiment. Firstly is the copper coil, second is the ring magnet, and third is the multimeter. First of all, we connect the positive probe, which is the red wire, and the ground probe, which is the black wire of the multimeter, to each end of the copper coil.
Now let's see this law in action. Here we have our copper wires coil connect to a multimeter. The multimeter will measure the voltage induced in the coil. As you can see, the multimeter currently reads 0 volt. This is because the magnetic field around the coil is constant. There's no movement and thus no change in the magnetic field. As we move the magnet toward the coil, the multimeter shows a voltage spike. This indicates that an EMF is induced in the coil due to the changing magnetic field. Then we move the magnet away from the coil. Notice how the voltage reading changed again. This change is due to the varying magnetic fields as the magnet moves. And this is Faraday's first law of induction in action. Thank you for watching. I hope you enjoy this demonstration.
Let me explain the theory of Faraday's law. In this equation, the change in magnetic flux respective to time inside the coil is directly proportional to the number of turns of coil and inversely proportional to the resistance of multimeter and coil. It is also equals to the total voltage drop around the circuit. So, the integral of the EDL around a closed path is the sum of voltage around the closed path. So, Faraday's law tells us that the sum of voltage around the enclosed path is not zero if there is a change in magnetic flux with respect to time. That's all from us. Thank you. These are the references that we refer to.